Similar to the last activity, here we're going to design a controller to achieve two frequency domain specifications. Go ahead and open up the CISO tool and attempt to solve this problem using proportional control, PD control, and lead control. As you started to work through this particular activity, you'll notice that even using proportional control, is able to achieve stability for all values of k. So that's a nice property. We can see that by the fact that the gain margin is infinite because the phase never reaches 180 degrees. But we do observe that that we have, again, this conflicting design goals. And so at low gain, we end up having poor response times, which we can see through the closed loop bandwidth. And at high gains, we end up getting pretty low phase margins. And so we look to more sophisticated controllers in order to do better. So we're going to take a look at, for example, lead compensators that might look like this, what this is really doing is it's allowing us to add some phase in order to help us out to avoid these very low phase margins. And so here what I'm doing is I've overlaid the Bode diagrams of several different controllers. So we have the proportional controller. In black, we have a lead compensator where the pole is located at -5, another lead compensator where the pole is at -20, and then we take a look at the PD controller as well, all with the same zero value. And so what you're observing is, as we go from proportional control to the lead controller at -5, lead controller with pole at -20, up to the PD controller, we're getting poorer. Essentially, we're losing in noise rejection, because essentially the magnitude here from 0 down to these lines represents how much that frequency is attenuated. Now, this is still achieving pretty decent performance because we're down at a magnitude of about -50 dB, so that's not too bad. And the fact that most of these solutions don't really start diverging until here indicates that the noise characteristics are going to be mostly suppressed based on this. But we are losing a little bit of noise suppression, but at the same time we're gaining that same curve following here, gains in phase margin. And so going from proportional control, which is this black curve, which is very close to 180 degrees here, we get a huge boost just by doing any of these controllers. The PD controller is going to give us the most phase, but it's also the one that reduces the noise attenuation the most. And so just like similar examples that we've looked at previously, there's this natural trade-off. And so one of the things we also want to avoid is this peak. We talked about this very briefly, but this peak represents, this resonant peak represents some overshoot. It's proportional to overshoot that we might exhibit. And so even though we don't have a constraint here, it's a good idea to try to avoid increasing this peak. So what you notice here is that the magnitude here, this is magnitude 1. And so what we'd like to do is avoid having too much of a peak right here that would lead to larger deviations. So one of the ways that we think about placing our controller, so when we talk about this numerator 0, it's going to be closer to the origin than the pole because it's a lead compensator. So that means that our pole is going to be out here somewhere or out here somewhere, and our 0 is going to be located further in at smaller omega values. And so because the way that the Bode magnitude of the 0 looks like, we'd like to place that to the right of, so we'd like to make sure our 0 is located somewhere to the right of this peak, because otherwise it would actually increase the peak value. So it's just something to keep in mind. Another practical constraint that's not explicitly in our specifications here, but something that we could pay attention to as we select from the several controllers that achieve our two design goals.